Hello and welcome to our first class at EPFL on numerical methods for conservation laws. This is a master class, and as the title already indicates, this is about numerical methods in the first place. So this is about computer simulations, how to do analysis on a computer, and in this setting, conservation law always refers to a partial differential equation. It is said that the vast majority of mathematicians is working on some topic related to partial differential equations, and certainly a large chunk of research on partial differential equations is about numerical methods. In particular, we will require some background in analysis for this class, so some understanding of basic concepts of partial differential equations, but of course the focus will be on numerical methods, how to approximate the solutions of those partial differential equations on a computer. How to do partial differential equations on a computer. The term conservation law is used throughout mathematics in different capacities. But in the context of this class, conservation law carries a very specific meaning. So for the purpose of this class, a conservation law is a partial differential equation, PDE, of the following form. The time derivative of uxt plus the divergence of f of uxt equals 0. Here, u is the unknown function. And okay, first we've got the time derivative, and then we add the divergence, where the divergence is taken in x of this flux function f. Now, the flux is quite important. It depends typically on u itself, but may also depend on x and t. Many different conservation laws arise from different choices of the flux function f. So that is a partial differential equation that we will consider and study within the next months. As you can tell, this is a first-order evolution problem. And generally speaking, what we do in this class is we study the existence and uniqueness of this partial differential equation. Some things we will encounter are weak solutions, entropy conditions that constitutes a theoretical background. Then we will also encounter and study some qualitative properties of conservation laws. That includes shock waves and, of course, a background in physics, which is often helpful to have an idea of how these partial differential equations actually behave. And of course, the focus of this class is on numerical methods. We'll take a look at finite difference methods, finite volume methods, and discontinuous Galerkin methods. You may have encountered some of those already in your classes on partial differential equations. You might have seen, for example, finite difference methods for elliptic problems. And chances are that you've already seen numerical methods for ordinary differential equations. Very soon, we will also encounter again time-stepping methods such as the Euler method or Runge-Kutta methods. So let's have some general remarks. This is obviously an evolution problem, which means it is time-dependent, and consequently, we always need some initial data at time t equals 0. What's more, generally speaking, we know the initial data and the flux function, and what we want to know, what we want to approximate or compute explicitly, is the unknown function uxt. The flux, in many cases, only depends on the function u itself, but at least in principle, the flux may also depend on the position x and the time t. Also quite important is that the unknown function u can be a scalar, just a real-valued function. In that case, we have got a scalar conservation law, or it might also have multiple components. In that case, we deal with a system of conservation laws. Of course, in practice, we always look at a spatial domain in some d-dimensional space. That might be a straight line segment, some domain in 2 or 3 dimensions. And we are interested in the behavior of the solution over a finite time interval. Let's say from some starting time 0 up to some final time t. In fact, most of the discussion here in this class will be about one-dimensional conservation laws. So in many cases, the spatial domain is just a line segment. As a first example, let's have a look at a scalar conservation law in 1D. So suppose we've got some quantity over some spatial interval, a one-dimensional line segment, and we let uxt denote the density of some substance at position x and time t. Then the total amount of the substance over some subinterval from x1 to x2 is given as follows. Let's denote the total amount in the subinterval by m of t, and that equals the integral from x1 to x2 of the density uxt dx. If you've got the density of some substance, then the integral will give us the amount of the substance contained in the integration area. That's just our good intuition from physics. Now let's suppose that axt denotes the velocity of the substance at position x in time t. Then some physical intuition gives us the following. We are interested in how the amount of the quantity contained in the interval changes over time. And mathematically, we express this as a time derivative of this integral from x1 to x2 of the density uxt dx. So how does this change? Well, we know that at the endpoints, the substance travels with some velocity given by a. For example, at the left endpoint, the density is ux1t, and it travels with velocity ax1t. If a is positive, substance travels in, and if a is negative, substance travels out. Similarly, at the right endpoint, the amount leaving is given by ax2t times ux2t. At the right endpoint, when a is positive, then some quantity is leaving, moving to the right, and if it is negative, it is moving to the left. Some quantity is flowing into the subinterval. So to summarize, the rate of change of the integral is given by the difference ax1t times ux1t minus ax2t times ux2t. But if we have got a sharp look at this difference, we recognize something. That difference equals the negative integral from x1 to x2 of the x derivative of the product axt times uxt dx. Why is it so? Well, this is just an application of the fundamental theorem of calculus. So to summarize, we can pull the time derivative. We can pull the time derivative into the integral. And so we got the integral from x1 up to x2 of the time derivative of uxt dx equals the negative integral from x1 to x2 of the x derivative of the product axt times uxt dx. That identity is valid at any time t and over any subinterval from x1 to x2. So in particular, if we now take infinitesimally small subintervals, then we get a pointwise identity. Time derivative uxt equals negative x derivative of axt times uxt. So that's a conservation law. In that context, what is the flux? Well, the flux is a function f of uxt, and it equals axt times u. So in that example, in principle, the flux can also depend on x and t. The preceding example was an example for a scalar conservation law that is also known as a transport problem. We will soon have another look at transport problems, but in the meanwhile, let's have a look at an example for a system of conservation laws. In fact, such a system of conservation laws arises already from a partial differential equation that you should be very familiar with, namely the one-dimensional wave equation. You could say that the one-dimensional linear wave equation describes the vibration of a one-dimensional string. So suppose I've got my x direction, which represents a base position of a one-dimensional string. In a very simplified setting, I can assign an excitation E to each position of the string, which represents whether the string is displaced upwards or downwards. For example, in this graphic here, supported by a PowerPoint stock image, we find an excitation that starts in the positive, goes downward, and then bends upwards again. At the position indicated, the excitation E is negative. Now, what is the one-dimensional wave equation again? The one-dimensional wave equation connects the velocity of any position in the y direction with the curvature of the graph in the x direction. What it says is the following. At any position x in time t, we take a look at the second derivative of the excitation E in the time direction. The second time derivative of the excitation tells us in which direction and how much the graph accelerates in the y direction. And the idea that is the background of the one-dimensional wave equation is that this acceleration is proportional to the curvature of the graph. That is, it's proportional to the second x derivative. So here in this context, gamma denotes a proportionality constant. At the position indicated here in this picture, you can tell that the second x derivative is positive. After all, the slope in this basin is only growing, which means that the second x derivative must be positive, and accordingly, the acceleration at this position is upwards. And that's pretty much what you would expect intuitively. So what does that have to do with the conservation law? Because this one-dimensional wave equation in one dimension, without any external forces, the second time derivative of E minus gamma times the second space derivative of E equals 0. To rewrite this as a system of conservation laws, we introduce auxiliary variables for the first derivatives. So let's write V for the first time derivative of E and S for the first x derivative of E. These correspond to the velocity and the slope of the graph. I claim that these satisfy two equations. The first equation that we have is that the time derivative of s minus the x derivative of v equals 0. Why is that the case? Well, that just expresses the idea that we can exchange partial derivatives. If we first take the x derivative and then the time derivative, that is the same as taking the time derivative and then the x derivative. And the second equation states that the time derivative of v minus gamma times the x derivative of s equals 0. And of course, that's just immediately derived from our wave equation. So that looks like a conservation law. Can we put it into this canonical form of a conservation law? Now it makes sense to write this as a vector with two components. Let's say we put the x derivative in the first component and the time derivative in the second component. We can rewrite this entire thing as follows. The time derivative of the vector SV plus the x derivative of the flux equals 0, where the flux has the following form. It's a matrix vector product. The matrix has the entries 0, -1, minus gamma, and 0. And the vector that we multiply has just components s and v. If you want to bring this into the canonical form of a conservation law, you've got the vector u with components s and v, and we've got the flux depending on the vector u, and formally also depending on x and t. And the flux just takes that matrix and multiplies it with the vector u. We've been talking about conservation laws in the sense of partial differential equations. But why are those partial differential equations of that specific form actually called conservation law? Let's have a look at that. Suppose that we work within some d-dimensional setting and let little omega denote a small domain. And again, suppose that uxt describes the density of some quantity distributed in space. Then the integral of uxt over omega dx describes the amount of quantity contained in that small domain. How does this amount change over time? In other words, what is the time derivative of uxt integrated over the small domain omega? Now, in many physical settings, there's a flux field, depending on u, x, and t, that describes the flux of the quantity at any given position and time. The physical intuition is as follows. The negative divergence of the flux describes how much of the quantity is created or lost in the small domain omega. We formalize it as follows. We have got the time derivative of the integral of uxt over omega dx. Well, first we can just pull in the time derivative into the spatial integral. So we integrate the time derivative over the small domain omega. And now we use a very similar argument as we have used before when discussing this one-dimensional scalar conservation law, but this time in a multidimensional setting. Namely, this rate of change equals the negative surface integral, where we integrate the flux times the outward unit normal. That perhaps requires some geometric intuition. We will come to that on the next slide. But if we just accept this physical intuition, then we can use the divergence theorem. And so the surface integral can be written as the integral of the divergence. So what we get is the negative integral over omega of the divergence of the flux, f uxt dx. And in some sense, that's just the multidimensional version of the fundamental theorem of calculus. So from that discussion, we can distill the following balance equation. Similar as before, going to an infinitesimally small domain omega, we can derive a conservation law in the sense of partial differential equations. And essentially what we've used here is the balance equation. The time derivative of the integral uxt dx equals the negative surface integral of f ust times the surface normal in ds. So in practice, such balance equations are the starting point, and that leads us to conservation laws in the sense of partial differential equations. In particular, if you've got a setting where the right-hand side, the surface integral vanishes, then we know that the integral of the quantity u actually remains constant, which means it is a conserved quantity. So what is the intuition for the balance equation? We've used that in a simplified setting in one dimension, but let's just have a look at a small graphic to describe it also in higher dimensions, for example, in 2 dimensions. So what you see here is a small domain omega, and the red vectors here indicates the outward surface normal of unit length. And let's suppose we've got the quantity flowing in the direction and velocity given by this green vector field. At the upper side of the picture, the green vectors are in the same direction, roughly, as the red vectors. So their scalar product, the dot product, will be positive, and that corresponds to some quantity leaving the small domain omega. By contrast, at the bottom side of the picture, the green vectors are in the opposite direction, more or less, of the red vectors. The flux is in the opposite direction of the normal vectors, and that corresponds to the setting where the dot products are negative. In other words, some quantity is entering the subdomain. And to the left and the right, more or less the flux and the outer unit normal are orthogonal to each other, which corresponds to the fact that nothing is flowing in or out. Now, with regards to scalar conservation laws and systems of conservation laws, let's have a more detailed look at the flux. If U is a scalar function, then U depends on a d-dimensional variable and the time variable. So one variable in R to the d and then a time variable. And it produces a real number. So far, so good. And the flux, in principle, depends on U, on the d-dimensional x variable, and the time variable. And the flux, being a vector field, must take value again in d-dimensional vectors. After all, if you want to take the divergence of the flux, then it must be a spatial vector field. Now let's compare that to the setting of systems of conservation laws. If U has got multiple, say, m components, then U is a function in the x variable, the d-dimensional x variable, and the time variable, and produces an m-dimensional vector. What is the flux? The flux, of course, depends on U, which is an m-dimensional vector. It depends on the d-dimensional x variable and the time variable. And what the flux F produces are matrices of size m times d. So in that setting, in the setting of systems of conservation laws, the flux is a matrix field. Generally speaking, the flux is a matrix field. We got m rows corresponding to the m components, and each row has got d entries corresponding to the d-dimensional space. Now, in this canonical form of the conservation law, we take the divergence of the flux, and in the setting of systems of conservation laws, that divergence is understood to be row-wise. So the flux produces this m times d matrix, and then we take the row-wise divergence of this flux field. Of course, one might say it's a bit of a technicality, but I think it's important to get this straight right at the beginning, so that later on we know what we're talking about and what class of objects we are talking about. What's more, speaking of systems of conservation laws and d-dimensional domains and conservation laws in d-dimensions, conservation laws get more complicated if we increase the dimension, and they also get more complicated the more components there are. The most simple setting, our starting point, one-dimensional scalar conservation laws. And those are pretty well understood now. Things get more complicated, more complex as we increase the spatial dimension, and they also get more complicated if we increase the number of components. So there's some research of scalar conservation laws in 2- and 3-dimensional domains. There's some research on systems of conservation laws in a one-dimensional setting. However, things get much more complicated if you've got systems of conservation laws in high-dimensional settings. In fact, even though we know some numerical methods for those settings, there's very little understanding of those numerical methods in this very general setting. So in this class, we focus most of the time on scalar conservation laws in one dimension. We take a look at scalar conservation laws in 2 and 3 dimensions, and we take a look at systems of conservation laws in 1 dimension. But we leave out the more complicated setting. So much for now, until next time.